Hi everyone, I'm Joe Albahari, over from Perth in Australia. I'm the author of C# in a nutshell, and if does anyone here use LINQPad? I hope that's good show of hands. It's actually, Norway is the second highest per capita user of LINQPad in the world. It's one of your neighbors is their highest per capita. So I want to ask, who remembers doing this as a kid? Long multiplication is something our parents or teachers taught us to do, and they programmed us to do this in the same way that we program computers, right? So they pretty much fed us an algorithm. You multiply this number by this number, and you put this digit here, and you add these things up together, right? That's an algorithm, and if we were to program a computer to do this, and that's not such a silly question, because the first computer I ever had, I programmed in machine code, and there was no multiplication, so I ended up doing something kind of like this to multiply numbers. And you're pretty much going through the same kind of algorithm you would go through the way we were taught to do this. But we take it for granted that when we learned to do this, we already knew how to recognize that that was a 4, right? And how is it that we knew that? Our parents didn't program us like a computer with an algorithm to do this. We learned through example. Just by seeing lots of these digits, we figured it out, right? Now, if you want to get a computer to recognize handwritten digits, and you were to come up with an algorithm, that's really difficult to do, right? So why can't we get the computer to learn in the same way and learn by example? And that's exactly what machine learning is, right? With machine learning, we have lots of input and output, and it works out the algorithm gradually just from looking at lots of samples. And a particular kind of machine learning algorithm is an artificial neural network. As with nearly all machine learning architectures, you can kind of look at it like this. There's an algorithm there whose behavior depends on a whole series of internal constants. These are that's floating point numbers. And then as we train it by feeding in lots of samples, it works out the optimum values of all of those constants. It's effectively how it works. So a machine, an artificial neural network, they're arranged like this. So here's an example. On the left, these white circles, these represent the inputs, and they might correspond to all of the pixels in an image. So you might have values from 0 to 255 to represent the level of gray, the grayscale. Then that connects to another layer of neurons, which then connects to another layer, which is where we get the output from. And we'll go into this architecture in more detail later. But the important thing for now is that those internal constants are represented by the sensitivity of the neurons. We call that the bias of the neurons. And the strength of the interconnections between the neurons we call the weights. And if we represent those by colors, this is what the training looks like. We start out by initializing those weights and biases to small random values. And that's why they all look gray at the moment, because the color is going to represent the weights and biases. Then we feed one of these numbers into this, like a 4. Now, because it's untrained, it's going to get that wrong. It might think it's 7. So then we ask the question, what adjustments do we need to make to those weights and biases to make it a little bit less wrong? We just make some really small adjustments to it. Then we do the same with another sample. And then we put a good 50,000 samples through that. And that's called an epoch. When we're finished, we shuffle those up into a different order and repeat it again. And after several epochs, gradually the weights and biases start to take shape. It starts to settle down into a set of values that lets us correctly infer the characters. That's essentially in a nutshell how it works. So if you want to do this, most people will go out and use a library, because there are numerous libraries to do this. And these libraries are the product of years of R&D, and they do things that you can't easily do yourself, like make use of the graphics processing units in your computer. Problem is, when you start using these, they're very powerful, but they're all black boxes. It doesn't really help you understand how they work. It's not particularly interesting, as in it's all hidden away. And it's rather like, if you've ever played with a flight simulator and you start out with something like that, and it's really cool. You follow the instructions, and hopefully if you've got all the configuration correct, you can take the thing off and fly it. You get one little thing wrong and it crashes or doesn't get off the ground, and it's not very satisfying. You don't know what you're doing, and you come back a week later and you've forgotten everything, right? Because you never really understood what was going on. It's much better after a while you go back to this. You start to learn how to fly that, and you really get to understand the principles of flying. And when you come back to this, everything makes a lot more sense. It's a lot more fun. In this session, we're not just going to fly this, we're going to build it from scratch, right? So starting from the lowest unit, which is a neuron. So a neuron has one or more inputs. It needs usually at least 2 to be useful. And all these inputs and weights, everything, these are all real numbers. Has one or more inputs, and it also has a bias. So when we fire the neuron, we apply some numbers to the inputs, and we multiply them by the weights and add up the bias. That gives us a total input. Simple linear arithmetic. Then we put it through a non-linear activation function, and we get the output. That's essentially what a neuron is. Now, the simplest kind of neuron is called a perceptron, which uses, for the activation function, a comparator. It asks a very simple question: is the total input greater than 0? If so, it outputs a 1, otherwise it outputs a 0. So let's give an example. We're going to create a neuron, and we're going to initialize the bias to 3, and each of the input weights to -2. And I'm going to put some numbers in. And to make it real simple, we're just going to put binary numbers. But of course, we could put anything in here. We can put large, small, positive, negative, floating point numbers. So let's go through the maths with this. So we multiply each of those inputs by the weights, and then we add in the bias. So that gives us a total input of 1. Now, 1 is greater than 0, therefore we output a 1. Now, if we just swap those 2 numbers around, we're going to get the same result because these 2 weights are the same, right? So we could 0, 1, or 1 or 0, we're going to get the same result as before. Let's put 2 zeros in there. Right now, when we do the maths, the total input is 3, which is still greater than 1, so we output a 1. And let's now put 2 ones in there. The total input is now -1, right? That's less than 0, so we output a 0. So what we've done here is we have created a NAND gate, a logic gate. Now, with a NAND gate, you can build any other kind of logic gate from a NAND gate by combining them together. So we can do anything with this. This is infinitely powerful. However, we have kind of cheated because we pre-program the weights and biases. Remember, what makes this interesting is this can learn. This can figure out the weights and biases through example. So let's play that out and see what happens. We're going to now initialize these now to small random numbers. These are actually quite large, but for the example, this will work fine. So I've initialized them now, and now we're going to put a couple of numbers in, 0 and 1, and we're going to play that through, and we're going to get an output of 0 in the end because the combined inputs minus 0.4, that's less than 0, so the output's 0. The correct answer is a 1. So we've got this wrong. So what we ask is, what small adjustments do we need to make to the weights and biases to make this a bit less wrong? Problem is with the way we've done it here is if we make any small change we make to the weights or biases, we're going to get exactly the same answer. Because we're either right or wrong. There's nothing in between. There's no grayscale. This is not conducive to learning, right? It's either off or on. So if we look at that comparator function and we plot it, it's like that. Right? If we want to make it conducive to learning, we need to make it more like that. So now there's this kind of intermediate area, this gray area. So if we don't get it right, we can see the direction we need to go into in order to get to where we want to go. This is called a logistic sigmoid. And this is a popular function with artificial neural networks. But the problem with it is if you look at the formula for that function, that's quite expensive to compute. Now, sometimes we're going to be using 50,000 samples. There are some neural networks that we're working with millions, right? And with over many epochs. That's very wasteful. So over the years, people have experimented with other functions. And what they've found is that there's something that works really well that's really cheap to calculate. It's more complicated to pronounce than it is to calculate. And it's called a ReLU, or rectified linear unit. And it's simply x equals y if x is positive, or 0 if x is negative. Variation on that, which works in most cases slightly better, is a leaky ReLU, where if x is negative, we divide it by 100. Right? Gives us a little bit of a slope on that side. Right? So if we now plug in a leaky ReLU or a logistic sigmoid into our neuron, we can now train it. The only thing we have to be careful of now is that in the end of the day, we still need to interpret the answer as a 1 or a 0 because we're trying to write a NAND gate. And so it's pretty simple to convert this continuous output into a discrete output. We just say, we want a 0 or a 1. What's it closer to? So if it outputs a 0.2, that's closer to a 0. We'd say, we'll treat that as a 0. Anything greater than 0.5, we'll treat that as a 1. Right? But what we've gained is the ability to measure the error. If it gets it wrong, we know how wrong it is and what direction it needs to go to be less wrong. So in this case, let's suppose the desired output is 0, the actual output is 0.2. We can say the error is 0.2. We define the error as the actual output minus the desired output. Notice the error can be positive or negative. Now, it would seem reasonable that our goal is to minimize the total error across all training samples, right? Problem is, that won't actually work very well at all, right? And to see why, we'll go through an example. We imagine this is one training sample. Imagine our other 3 training samples, we get exactly the same output. We get 0.2 for all of them, and imagine that the correct answer is 0 for all of them. So it got all of them correct, all of them, we have an error of 0.2. Right? If the error is less than 0.5, we'll go back a slide. If the error is less than 0.5, we get it right. Error is more than 0.5, we get it wrong. So in this case, 4 of them, error is 0.2 and all of them, we got them all correct. Imagine another scenario now. The first 3, the error is 0, but the last one, the error is 0.6. So now it's got one of them wrong. But look at the total error. The total error is lower in the second case. So if we program the machine to minimize the total error across all training samples, it's going to favor that second outcome over the first outcome. Right? It does exactly what we tell it. So what we need to do instead is we need some way to punish the big errors more than the small errors. The easiest way to do that, and by far the cheapest, is to square the error first. Right? So if we square all those errors before adding them up, the first case we get 0.16, the second case we get 0.36. So now it will favor the first case. So now we're no longer minimizing the total error. We need another term to describe what we're minimizing. And the term that we use is called the loss, right? Or the cost. That's a synonym. Right? The loss is whatever we're trying to minimize. We can define that loss function however we like, but the most popular loss function is the error squared. Simple and easy to calculate. Right? A few nuances. Rather than defining loss as the sum of the error squared, we usually define it as half the sum of the error squared. That makes no difference. Whether you minimize x or you minimize half of x, you're going to end up in the same place. The difference is it creates a nice mathematical simplicity and symmetry that we'll get to later. Another nuance is we could also, instead of calculating the total, the sum of the error squared, we could calculate the mean of the error squared. Again, exactly the same result. You'll sometimes see the term MSE, mean squared error. That's exactly the same thing. Another interesting thing is that we don't usually calculate the loss. Right? How many of you here drive? That's a lot of hands, I guess because the taxis are so expensive here, right? Right? Now, most of you will probably consider yourselves good drivers. And yet, if I were to ask you, what is the probability you're going to have an accident on the way here? You're not going to be able to give me a number, right? And yet, you could be constantly doing things every day to monitor your safety and improving your safety. You can minimize something and improve it without actually measuring it. right? So in the same way, if you look for the code that measures the loss in this, you won't necessarily find it because we don't actually need to calculate it in order to minimize it. So let's get back to our example. We'll plug a leaky ReLU in now to our neuron. So we're going to initialize it, again, with small random values for the weights and biases. I'm going to put a 1 and a 0 in there. The combined inputs now are 0.3. Now we plug it into that leaky ReLU. Now what should the output be? If the input's 0.3, and you plug it through a leaky ReLU, what would the output be? Yeah, that's it, 0.3. It's greater than 0. Anything greater than 0, we just take the x equals y. So it's 0.3. Now, the correct answer, of course, is 1, right? 1 NAND 0 is 1. So the actual output is 0.3. We can now quantify the error as minus 0.7. So we can see now that what we need to do is increase the output. How do we know? Because we always want to go in the opposite direction of the error, right? So we want less of the error, not more of it, right? So we've flipped the sign, we want to increase this. And maybe if we could make this 0.301, that would be a good thing, right? Just to wind back a step, we want to adjust these weights and biases, right, to make this a bit less wrong, but we need to know first, how do we adjust them? To do that, we start from the right and we work backwards, work from right to left. So we start with this and we say, well, the error is negative. That means we need to increase this slightly. So it'd be good if we could make this 0.301. We can't control this, but we can work backwards. So we can say, what do we need to do to this combined input over here? And because we're on the positive side of the ReLU, when the x equals y, it's exactly the same thing. So if we increase the output, that means we also need to increase the input. If we're on the leaky side of the ReLU, right, then we will be dividing by 100, right? So it would be a bit different. So we need to increase the output. So remember, this is for one training sample. We've got 3 others, and then we're going to go over them again and again and again. Right, so we've got to take into account the wishes of the other training samples as well. So one way in which we could do this is we could repeat this exercise for the other 3 training samples and take votes, saying who wants to increase the bias, who wants to decrease this weight. And then whichever gets the most votes wins. And then we make an adjustment and continue. But problem with doing that is we would be minimizing the total error, not the total loss. If everyone gets 1 vote, then it doesn't matter whether you really need to make an adjustment or not, right? You're all getting the same say. And so we need to be a bit smarter in how we do it. So what we do instead is we give a variable number of votes to each training instance. And that vote is simply the negative error. So this one gets 0.7 votes because it's out by 0.7. If the error was minus 0.1, it would only get 0.1 votes. So that way we take much bigger action when there's a bigger necessity, right? When there's a bigger error. Right, so if the output gets 0.7 votes, the input gets 0.7. We're on the positive side of the ReLU. If it was on the negative side of the ReLU, the input would get 0.007 votes. We would divide by 100. That would mean that we would be doing almost nothing. Right? We'd be making almost no changes, which is what we want. Right? When you're training these things, you want to be very careful, because if you make any change you make can break it for other training samples. So if it's not going to make any difference for you, you don't want to break it for anyone else. Okay, so the input gets 0.7 votes. Now we could now go to all the other training samples and collect up the votes, but we don't need to. There's an easier way to do it, right? If we were to do that, it's called batched learning, where we collate it for all of the samples. But there's a more popular and more efficient way called stochastic learning, where what we do is we make a small adjustment after every training sample and move on. And the end result is similar to what we get if we added them all together and made one adjustment. So in this case, the step size is called the learning rate. At a learning rate of 0.01, multiply that by the input votes of 0.7, the adjustment's 0.007. So now what we do is we take that bias of 0.1, that now becomes 0.107, we add it to that, and we also add it to this weight here, which becomes now 0.207. The second weight, however, you notice I've not made any adjustment to that at all. Why not? Why haven't I adjusted that weight? Exactly, it doesn't change the output. And why doesn't it change the output? Because this is 0. It gets multiplied by 0. Remember, we don't make adjustments unless it's actually going to help us, because all we'll do is mug it up for the other training samples. So we've done that training sample. We've made some changes to the weights and biases. We just keep repeating that for all of the training samples over and over, and that's all there is to training a neuron. We've covered the whole algorithm for stochastic gradient descent. Right? So before we code it up, though, I'm going to go in a bit more detail on a couple of things, right? Just for the sake of mathematical curiosity. One is to explain how it is that we're actually minimizing the square of the error, even though we didn't calculate it. And the other thing is to explain why it is, how we deal with this ReLU. Why is it that we multiplied by what is effectively the slope of this function, right? We were multiplying. Right, the output got 0.7 votes, the input got 0.7. We multiply by the slope of this function wherever it is. Now, to explain that, let's switch to a logistic sigmoid, right? If we used that activation function, the black line shows you what the function looks like, and this grey line shows you the slope at any point. So when it's right in this point where it's switching off and on, it's got the steepest slope. So it's going to get the most activity. So the input, any changes in the output will affect the input significantly. But on either side, if it's over here or it's over here, it's kind of switching off. It's not any changes in the output are not going to make much changes to the input. So explain how this works. Imagine you're a politician, and you're trying to decide on a policy for whether Norway joins the EU, because apparently there's a vacancy coming up soon. So you go from constituency to constituency, visiting all your electorates, gauging the public opinion on that, gathering votes. But you're not going to treat all electorates equally. Right, there's some people out on the streets demonstrating, you know, EU, 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 other words, no EU, no EU. And you go to another electorate and they're meh, don't care one way or the other, right? The strength of the sentiment is very important. So that will be equivalent to the output votes, is the strength of the sentiment. As a politician, you're a neuron, you're learning as you go from electorate to electorate. Each time you go, you adjust based on the output votes. So do politicians have an activation function, right? What you're doing here, when you're multiplying by the slope of this function, you're applying the chain rule in calculus, right? If you didn't understand the chain rule before, you know it now. So do politicians do this? Do they apply the chain rule when they're trying to decide policy? They most certainly do, right? Politicians focus their efforts into where makes the most difference, right? Where that slope is the steepest, right? That's where they make that's where it has the greatest say. So often they'll decide policies. Maybe this is in Australia. I'm sure it's not like this in Norway, but often they'll decide policies to please the marginal electorates, right? Even at the expense of upsetting some safe seats or unwinnable seats, right? Because that's how they can win the election. So that's pretty much how it works in terms of the activation function. Now, in terms of how is it that we're calculating the square, the loss, the minimizing the loss rather than the error, I've plotted here a graph showing you the error in green, and on the x-axis is the input. So when the input was a 0.3, the error was minus 0.7. And you can see that if we shift the input to the right, that's going to improve the error. Now, let's plot the loss function on here. Remember, loss is half of error squared. That's what it looks like. Now, it just so happens, very nice coincidence, that at every point on that graph, the slope of the loss function is exactly the error, right? Because when you differentiate half y equals half x squared, you get y equals x. So what we're doing is when we take a step to the right, in proportion to the error, we're taking a step in proportion to the slope of the loss function. So you imagine that you're sitting, that's a slide, you're sitting on that slide, you're going to go down at a speed proportional to its slope, right? And eventually you'll go down further and further, and then you'll slow down as you get close to the bottom because it's not as steep, and you'll settle down where that loss is a minimum. So you're doing a gradient descent on the loss. Even though we haven't actually calculated it, that's what we're doing. So because we're doing stochastic gradient descent, we only make one step before changing over to a different curve, right? Different sample, different training datum. Right, so we repeat the same thing. We might now go, the error now might be 0.35, so we now take a step to the left. It's only half as much now because the slope's only half as much as we had before. Okay, so the end result that we get is the same as if we were doing a gradient descent on the combined loss function for all of the samples together. So that's the maths behind it, and without too many symbols. So to summarize, for each training sample, we determine the slope of the loss function at the current position. Right? Remember, this is really easy in practice because the loss function is simply the error. It's minus the error. Right? And we step by the following amount, the slope times the learning rate, and that's it. So I think it's time to code something up. And we're going to do this in LINQPad 6, which is, I've released the first preview a few days ago. This runs on .NET Core 3. So on Preview 6. So it might be a little bit unstable, so bear with me. I've got LINQPad 5 here in case it all crashes and burns, so we can go to that. We'll see how it goes. So first thing, we're going to train this NAND gate. Let's have a look at the class. I've created classes for this. OOP is actually pretty good for writing this in terms of creating code that's fairly easy to follow. So I've hard-coded 2 weights. Our neuron's going to have 2 weights. It's going to have a bias. And I initialize the weights and biases to small random numbers. Now, when you're doing OOP, because part of the feature of OOP as contrast to functional programming is we have state and we mutate it, right? And we do that proudly because it's good for performance reasons in this case. But when you're doing it, you want some hygiene over your state. So it's very good to separate long-term state from short-term or transient state. By putting them in separate classes, it's good practice. And in this case, the long-term state is the weights and biases, right? This changes very slowly as we train it. And then once we've trained it, they kind of become constants. We can save them to a file and load them back up again, and they don't change while we're actually using it for inference. The transient state is all these temporary things like the total input, right? That's a transient. That's a transient state. So I've created another class called firing neuron, which captures that, or the transient state for inferring, for firing, and for learning. So to fire, we multiply input 1 by the weight of the first neuron, add together input 2 by the second weight, add up the bias. That's all there is to it, right? Then we apply the ReLU. So if the input is, this is the activation function, if it's greater than 0, it's a total input. If it otherwise, it's the total input divided by 100 if it's negative. Now, here's the more interesting bit. Here's how it learns. So they're given 2 inputs and an expected output and a learning rate, how we do it. So first thing, we need to fire the neurons so that we know what the output is. The second thing is to work out the output votes. Remember, all it is, it's the negative of the error, right? The error is the output minus the expected output. So the output votes, we just flip it the other way around, right? That's equivalent to to deriving the loss function, right? The slope of the loss function. Then we apply the chain rule, so we multiply it by the slope of the ReLU, right? So if the total input is greater than 0, we multiply it by 1. Otherwise, we multiply it by 0.01. And now for the input votes, we multiply that slope of the ReLU by the output votes. Right, so this is where we're applying the marginal electorate test, right? So if the output is greater than 0, it's like a marginal electorate. Otherwise, it's safe seat or unwinnable seat. So now we can work out the adjustment is the input votes times the learning rate. That's that small figure, and we add that to the bias, and we also add it to each of the weights. But remember, we always multiply by the inputs. So if the input's 0, it's not having any effects, so we don't want to make any adjustments. And if the input is negative, we want to adjust in the opposite direction. So that's it. That's all the code there is to it. So all of this stuff, you can download this. So if you go to LINQPad, go to samples, there's a link here called download, import more samples. You click on that link and then scroll to the bottom, and then it will there'll be a sample you can click on to download this. So we're going to, most of the code here is just creating test data and testing it. So to manufacture data, it's very easy. We don't have to download the data, we can make it up. We just create a whole lot of random pairs of zeros and ones, and then we know what the desired output is by applying the NAND function. So let's just dump this sample data first out to see what it's like. And we'll run that so you can see what the sample data is. So here we are, we've got lots of random inputs, and we know that's the NAND, that's the desired output. Okay, so that's how we start out. The next thing we need to do is we need to separate it into training and test data, because it's no good if we use all our data to train it, because then we won't know how well it performs in the real world. Because it might be that it works really well with the data that we've trained it with, but when we give it data it's never seen before, it screws up. So we need to know that it can generalize to stuff it hasn't seen. So we take usually 20% of the data, we lock it away, that's our test data, and the rest of the data is our training data. We're going to use 80% for training. So basically we're splitting it up into training and test data. We're training it now, we're calling the learn method on each of these, and then we are doing a report on how accurate it was. So let's run this now and see what the result we get. It's pretty quick. This tells us after 200, right? We trained it with 200. Let's go up to the top. Total samples, we fed 1,000 samples. We need a learning rate of 0.02, and it got, of all the 200, which remember we took 20% away for the test data, of all of those it got them correct. These are the final weights and biases. Bias 1.17, and the weights were negative 0.4 something. So that worked pretty well. Now, because we use small random weights and biases, each time you run it, it's going to be slightly different, right? But each time we run it, it always gets it correct. We can have a bit of fun with this. Let's say if we reduce the total samples to 100. What happens then? Does that work? It doesn't. In this case, it's got 6 correct. Sorry, it's got 14 correct and 6 wrong. So not enough. We need more than 100 samples. We can also try increasing the learning rate to 0.5. See what happens then. If the learning rate's too high, again, it's screwed up. Because if the learning rate's too high, it will oscillate. So you imagine you're on that slide and you're going down, you get too much momentum, you're going to go up to the other side again. You're going to keep oscillating. So that learning rate's too high. We can also try seeing, we can change the function on here and see, can we teach it to do NORs? If we change that to an OR instead of an AND, we can train it to be a NOR gate. And again, that works perfectly. The NOR gate. What about if we can train it to be an XOR gate? Let's try that. It's failed. It's got 100 and roughly the same number right and wrong. Train that again. It can't do an OR gate. So an XOR gate. We can't train it to do an XOR gate. Why not? Right, to do an XOR gate, it needs more than one neuron. Right, we need to feed the output of this neuron to the input of another neuron, right, to do an XOR, which leads us to the next part of the session, because I did promise you a Cessna, but so far we've kind of got a hang glider, right? So we're going to go back to the presentation, just so that we can see what the here we are. So this is now a network of neurons. So what we do when we connect them together, it's a pretty simple architecture. So all our inputs on the left, they're not neurons at all, they're just inputs, they just hold a number. Each of these holds the pixel value in one of these, in this case. And then we organize them into layers. On the right-hand side is the output layer. So we have one of these per possible answer. So in this case, if we've got 10 digits, we'll have 10 output neurons. So whichever one gives us the highest number, that's the one it thinks it is, right? And everything in the middle are called hidden neurons or hidden layers. And we organize them into layers. So the input for this neuron here, every input, every neuron in the hidden layer gets its inputs from every pixel, every of the input layer. And similarly, on this next layer here, on the output layer, every one of these neurons derives its input from the outputs of these neurons here. So it's a pretty simple configuration. Now to fire it, we go from left to right, right? It's called feed forward when we're firing it. So we start by firing all of the first layer of hidden neurons. And this can be done in parallel, right? It's very conducive to parallelization. So then we'll end up firing all of these. Now, once we've done that, we can now fire the next layer across, so we can fire all of the output neurons. And now, if we do that, we should get a whole lot of numbers if we feed one of them in there. And in this case, the number 8 is the highest, so it thinks it's an 8. If there was another one there that had, say, 0.4, it wouldn't really matter too much, right? So just as before, big errors are much worse than small errors. Small errors don't matter, right? As long as the highest one is the one at which it's supposed to be, we've done pretty well. So we're going to use the same loss function for character recognition. We're going to use the square of the error as a loss function. So when it comes to training this, again, it's pretty much the same as what we were doing before, but now we work backwards. We work from right to left. So we start by training all of these output neurons in exactly what we did before. The same process we did, find the same loss function. We know what the desired output is. We know what the actual output is. We train each of them in exactly the same way. And now we need to move to the next layer over here. In this case, we've got one hidden layer. And there's one piece of the puzzle we need, which is how do we work out what the output votes is for each of these hidden neurons, right? Because we don't have an expected output anymore. There's no desired output. And it's the simplest possible thing that can work. You take all of the neurons that it connects to here, all of their input votes, and you do a weighted sum. Right, so the weighted sum of all of these interconnections, that's all it is. Like anything that was simpler than that would be leaving out something. If we didn't weight it, that would be a bit weird. And if we ignored some of the neurons, it would be a bit weird. So it's the simplest possible thing that can work. So we're going to go ahead now, and I've coded all that up. And I'll show you what it looks like. Now the neurons got a bit more complicated. The only extra complexity, though, there's a lot more code in here, but it's all plumbing. It's just wiring things together. There's very little in terms of neuron logic in here, but I'll show you which bits are different. We've now got an array of input weights instead of just having two, and I've got the bias. I've also created a pluggable activation function. So instead of hard coding the ReLU, I've created an abstract class called activator, and you can subclass it. So I've got all the popular activation functions are there for you to play with. This is like a playground for neural networks with all white boxes. There are no libraries in here, absolutely no libraries, no config files, right? All here. So I'll show you now also that's our neural network, which contains layers of neurons. That's our firing neuron now. And again, compute with a function to compute the total input. Similar to what we had before, we do a weighted sum. This is the method to adjust the weights and biases. This is part of learning. Now, one thing you can do, and C# is great in terms of you can really easily parallelize something. And we want this to use all available calls. To do that, all you have to do is parallel.for. Right? However, there's a possibility of creating contention and a hotspot because we have to update the weights and biases. We're updating shared variables, right, these weights and biases. So we need to have a lock. So we want to minimize the time spent in that lock. So there's another nice feature of C#. You can use pointers when you really need this kind of performance advantage. This speeds it up about 30% by changing from using the arrays to using pointers. So that's our firing net. That's our feed forward. We just go from layer to layer, firing all the neurons. Can be called compute outputs. And here is the one thing, when it comes to the learning, this is the one extra bit of logic that's related to the neurons rather than to the plumbing. So for the hidden neurons, we need to work out how many output votes to give it. We take the weighted sum of the next layer to the right's input slopes, right, or the input votes. And this is where we're doing it. We're using the sum of all of the next layer's input votes times the input weights. So that's pretty much it. So that's the logic in terms of the, there's a few more minor things. I made little adjustments to the learning rate for each layer. I found that improves the rate at which it learns. So we need some training data. Now, fortunately, there's a public domain, a really good public domain data set called MNIST. This code automatically downloads it for you if you haven't already downloaded it. And it's nicely divided into 50,000 training images and 10,000 testing images. Right, so this creates a neural net. This is the number of inputs it has. Then I'll call them neurons, the number of inputs. Because they're square images, it's the image width height squared. This is the number of neurons in the first hidden layer, 20. And because we've only got one hidden layer for now, this is the number of neurons in the output layer, 10. So this is pretty dumb. It's only got 30 brain cells in total, but we'll see how well we can do with 30 brain cells. We're going to train it with a learning rate of 0.01 and 10 epochs. We're going to go over the whole thing 10 times. Let's run it, and then we'll do a report. Okay, so the first epoch, we've got a training accuracy of 93%. It's gone up to 95 in the second epoch. We're up to 96% now. This is pretty good for 30 brain cells. Right now, our final, after the 10 epochs, our final training accuracy is 96.5%. But what really matters is the test accuracy, because remember, how well can it generalize to stuff it hasn't seen yet, right? And it's actually done pretty well. It's still 95.6% accurate. Now, this shows us the failures of the highest loss. This is the things it had the most trouble with, right? And as you can see, that's I don't even know what that is supposed to be. Right, but that was supposed to be a 2. That was supposed to be a 6. It thought it was a 5. That was supposed to be a 3. Well, no, what was that? Yeah, supposed to be a 3. So on. So now, one of the things you can do in LINQPad is you can write visualizers. So you can, and I've written a visualizer for this. So when I call this, what it will do is it will show us all the states of the weights and biases as it's running. So when you dump this out, you can actually watch it learning now. So you can see it's starting to take shape now, the color. Right now, this is not showing you the inputs, it's showing you the hidden layers, because there's too many inputs to show you. It's showing you the hidden layers, and it's showing you the outputs. Now, on the right-hand side, we've got a canvas that we can draw on, because it's one thing to run it against the test data, but it's something else to actually, draw something on here. So wish me luck. I'm going to draw something. We'll see how it goes. So I'll put a 1 in there. It got that right, which was kind of surprising. Let's give another go. Oh, I thought it was a 7. That's all right. Got that right. Thought that's a 4. Was a 4. It's not doing terribly well, is it? Now, there's a problem here. This is something interesting because it's getting about 40–30% accuracy. How did it do so well with the training data and it's doing so poorly? And you don't have to look for configuration files or you've used the library wrong. It's all your code. It's all there, right? So there's got to be something you've done wrong. And this is really when you learn. When you run into this kind of problem, this is really when you learn how this stuff works. And when you look carefully at the samples, what you can see is that they're all being really nicely centered. That was part of the scanning process, is that they centered them. So this is being completely confused by the fact it's not perfectly centered. Right? So there's no danger of this taking over our jobs. So there's 2 ways we can solve this. One of them is we can do what's called data augmentation. We take all those samples and we shift them and we rotate them and put them up and down, left and right. So we get it to teach it how to deal with that. Right, that's one way. There's another way which is easier in this case, is which we can simply center this sample before feeding it into the neural network, which is what I've done here. So I've already done it. I just need to uncomment the code. So I'm going to take this off and run it again. SEH exception. External component. This is a bug in .NET Core 3 Preview 6. I'm not blaming it on LINQPad. Let me just have a quick look at that. Look away. I'm going to see what's the stack trace on there. Oh, yeah, that's in the WinForm stack. That's all right. Okay. So let's have a look now again and see how well this works. So it's done the 10 epochs, and it's got it right. Let's try something a bit harder. It's got that right. Got on. I haven't even finished the 5. It's got it right. So it's doing pretty well now, just with that centering. Now, one interesting thing is if I draw, I'm going to draw 7, I'm going to do it really carefully, like a typewriter would do it, like, really nicely. It can't get that because people don't write like that. It's never seen anything like that before. But that's completely confused it. Right? So this is interesting how it works. Because obviously we could train it with that kind of stuff. So we can actually improve it though, because we've got a final training score of 96%. And there's a number of ways we can improve it. One is we can create more layers in there. So I'm going to increase that to 30, but I'm going to add another hidden layer. So there's 2 layers in there now. We're going to train that. Forget about that exception. Yeah, we can see that extra layer in there now. This is using all the cores, so it's getting the fans starting up now on the laptop. It's quite a bit faster. If you put a new hex core or a 8-core machine in there, it runs quite a bit faster. Now you see this is going up. The training score's going up. We're up to 98%. Now, when you get more than 2 layers, we're now doing deep learning, right? That's way cooler than shallow learning. Okay, we've got a final test accuracy of 96.8. We've gone up a little bit, but to be honest, with this particular kind of problem, you can get the best result just by increasing the number of neurons, by having 2 layers rather than 3, and just increasing the number of neurons in that middle layer, just having 1 hidden layer. But something else we can do, because I told you we had a pluggable activation functions, what we can do is I create a new activation function in here. So I'm going to change the activation function on that middle hidden layer to an exotic one, soft max activator with cross entropy loss. Right, now that sounds really fancy, and it is. But what this actually does is it's not just changing the activation function, it also changes the loss function. It gives us a more elaborate one. We're going to train that, see how that goes. And while it's doing that, I'll cover a couple of other things, which is this gradient descent that we talked about before. That's a nice curve. It applies to a single trading sample, but when we take all of them into account, we end up with something way more complex, and you get this phenomenon called local minima, where you get, it can end up getting stuck in there. And this is one of the reasons why we initialize the weights and biases to small random values. So just by rerunning it over and over again, you'll end up in different spots. So you choose whichever gives you the best final result. But one way you can help avoid that problem is if you keep it simpler. So if you have fewer layers, fewer complexity in your function, what you end up with is you still get the local minima, but they're all quite close together. Right? So it turns into less of a problem. And what we're doing here is pretty simple, so we don't get too many of these problems. See how this is doing now. It's kind of slow, isn't it? That's running so slowly. What I'm going to do, I'm going to stop this. I'm just going to reduce this to 50 neurons. That is a much slower activation function. This is one of the things you have to, it's a trade-off you're making, and it doesn't matter whether you're using this or you're using a big library like TensorFlow, is that sometimes it's better to use an inferior activation function and loss function if it's quicker, because you can get way more iterations done. You'll end up getting a better result sooner anyway. So sometimes it's not always better to have the better function. It's training quicker now. And what you find with this is that with this activation function, we can get right up to 99%, 99.5% training score on there. But the problem is when it comes to the actual test score, it's no better than what we had before. And this phenomenon is called overfit. And what it means, it's done a really good job at fitting all of those training samples, but it can't generalize to stuff it hasn't seen as well as you'd like. And that's overfit. And that's what tends to happen with this exotic activation function and loss function. Right, we're 99.4% accurate on our training, but the test accuracy is only 97.8%. So we can actually get the best result for the final test accuracy by going for anything up to, I'm going to stop at 200, but we can, up to 1,000. You can put 1,000 neurons in that middle layer, and then that will get you about 98.5% accuracy, which given the simplicity of this is quite good. So while this is going, there's something else. Is it still going? Or as SEH exception finally got the better of it. It is going. Okay, so something else I want to do, which is what do we do if we want to get even better than that? Or we want to solve more difficult problems, like recognizing what kind of object, whether it's a fluffy cat or a dog in the picture. And the way these more advanced neural networks operate is unlike this neural network, which is a general purpose. You can use this kind of network to solve a whole variety of different problems. But what you can do is we can make this so that it's only designed for image processing and nothing else. And when you do that, you can end up with something which works a lot better for image processing. For instance, you could start by running, rather than feeding the raw pixels into the neural network, you can first run it through some filters and do things like edge detection and line detection, circle detection, and then you feed the output of those filters into the neural network. And that gives you quite a bit better result. Now, what's really clever about that architecture is that you don't have to you don't have to design those filters. All you have to decide is how many filters you want. Because when you write these filters, the way they work is you use matrices, which all it is a bunch of numbers. You can describe a filter which does something like edge detection just with a bunch of numbers, basically, which you put into a matrix. Now, once you've got a bunch of numbers in there, you can allow the neural network to figure out what values to put into those numbers through backpropagation. Exactly the same mechanism we did before, the backpropagation. You can get it to tune the filter. So it decides on the filters. You only decide, I want 10 filters. And initialize those filters to small random values, it will tune them. And that's called a convolutional neural network. And that's the basis of a lot of the deep learning networks today that do image recognition. Something else I want to describe, which is what to do if you don't have much training data, because we've got 50,000 in this case, and sometimes you don't have that amount. And there is a technique called pre-training you can do, or transfer learning, and that is that imagine that we wanted to now train it to do letters, or let's say we wanted to train it to do numbers. But we didn't have any numbers as samples, but we've got lots of letters. What you can do is you can train it first to do letters, which is a similar kind of thing. And then once you've optimally trained it, you can save all those weights and biases off to a file, right? So it can now do letters. And now, when you want to train it to do numbers, and you've only got a small set of numbers, what you can do is rather than starting out with random weights and biases, you start out with that pre-trained network you got that was capable of doing letters. And you find that it actually does a much better job because there's similarities between the letters and numbers. So it's kind of learned something in there that's kind of encoded how to do some recognition, and it's now applying that to a slightly different task. So it's called pre-training or transfer learning. Probably pre-training is a better term for that. And that's what's done it also extensively with the deep learning networks that you can play with, such as TensorFlow, is if you want to do an image recognition task, you can download something which has already been trained with millions of images on the internet. Let's go back to that and have a look. See how it's doing. It's getting very hot, I'll tell you that. So while that's going, any questions? We've got 5 minutes. Okay, the different colors in the lines represents on the neurons. the color represents the final bias of those, of the bias of that. So that's constantly changing. So that's the bias. And the color of the, it's hard to tell, there's so many of them, but the color of these lines is the weight, represents the weight. So blue is negative, and red is positive. Any more questions? It's hard to see here with the lights. Okay, so we've got a final test accuracy of now 98.3% and this is with 200 neurons on the hidden layer and 10 on the output layer. So we'll give it another go with, oops, I fat fingered that one, but that's worked. Yes, it's doing a pretty good job now. So this is similar to what you'll get even with some of the commercial ones. It's only slightly better than this. So yes, I'll be hanging around. So if you want to talk to me afterwards about this, you're welcome to come and see me. So thanks everyone for coming.